All right, and so let's talk about different notations. So we've talked about f primed of x or f primed of a, right? And that's our this is called Lagrange notation, and that's the most common notation, I would say. And a close second to the most common is this is called Leibniz notation. And so they're both pretty common. They're both used for the most part, I would say, in any textbook or class that you have, calculus class. And they're both have kind of different. They're both valuable in different ways. I would say Lagrange is the most user friendly, and maybe the most kind of yeah, I'd say yeah, mostly just user friendly. And then Leibniz has some cool kind of intuitive features to it. Like for example, and we say dy dx for this. So, but basically, this is kind of what's happening, right? Like slope is delta y over delta x, right? Change in y over change in x. That's what our slope formula is y2 minus y1 over x2 minus x1, right? If we go back to algebra 1, and then all of our derivative functions and our slope of the tangent line functions and even our secant line functions are all based off of this formula, right? And so, but basically all it comes down to is changing y over changing x, right? Like your rise over your run, okay? And so, so dy dx kind of encompasses that, right? Because it's delta y over delta x, but it's the limit as delta x approaches 0, right? As this distance gets super, super small, right? And remember, this point gets super, super close to this point. That's what the limit does for us, is it gets us once again that secant line, but where it's super, super close to the other point, or to the point where it's actually right on it, and we can evaluate that value, or we can find that value at that point. All right, so dy dx. Let's see, some other notations that are common are, and the other thing about dy dx is it kind of gives us an operator too. Like before we found the derivative of, what was it, x squared plus 2x, right? And so if I want to say take the derivative of it, you could do this. Sometimes people say that function prime. And another thing you could do is you could do d dx of that, okay? So you could take this is kind of the operator to say I'm taking the derivative of this function, right? Let's see, another thing, sometimes like if you just have a function that's y, like if I have a function that's y equals 2x or x squared plus 2x, then you could also say just y prime. So you don't necessarily have to say y primed of x or f primed of x. You can just say y prime. So, all right, and there's a few other notations out there. But if I want to do this, f primed at a, like at a given point, the way to do that with dy dx is you'd say dy dx, and then you use this this bar here, and you'd say x equals a. So that's it. Like this and this mean the same thing. And you can see why this is a little more user-friendly, right, in that way. All right, but this comes in handy when we're kind of validating things, or maybe even proving some different properties or rules or theorems. This Leibniz notation kind of helps us, and helps us to kind of see intuitively what's going on. Because ultimately the derivative is a ratio, right? It's the instantaneous rate of change. So it's a rate of the change in y over the change in x, right? At a certain instant. Now let's say we wanted to graph the derivative of a function given a graph, right? So if we're given a graph here, we don't know exactly what f of x equals, right? We don't know what this function is in terms of its algebraic form. So all we can see is this graph here, right? And we want to sketch the derivative. So we won't be able to sketch it exactly. We could actually, we could get pretty close if we really found, the slopes, and we had a good way to measure the slopes at each point. But that's what our derivative is, the slope at each of these points, right? Now, we did this a few times yesterday. One at the end of class with the one I showed you on the calculator, where we're looking for where the derivative equals 0. And we also did in the Kahoot at the beginning of class, right? And that's an important thing is to find out where the derivatives equal 0, because that tells you where your peaks and valleys are, right? And so if we're going backwards and we're sketching the derivative, then that's also a good way to start, is to know where your zeros are. Okay, so I have a 0 here, right? So somewhere right here looks like where x is equal to -2, that's a 0. And then where looks like where x equals 3, that's also another 0. Okay. Now the reason those are important is because if I'm graphing the derivative is going to equal 0 at those points. So I can actually just put dots on the x-axis, because that's where the derivative is going to equal 0. Okay. And so then what I do is, once I find the zeros and I mark those, then what I'm going to do is I'm going to mark what happens on either side of these zeros, right? So I want to know on this side of that first 0, what's happening. Is the derivative going to be positive or negative? So I want to look at the slope here. The slope is decreasing, right? It's going down to the right. So that means we have a negative. The derivative is going to be negative on this side over here. Okay, so I'm just going to put a negative here. All right, now between here and here, the slope is going up, right? It's going up and to the right. It's increasing slope. So that means the derivative is going to be positive, right? The rate of change is going to be positive along all these lines, or along all those points. And then the last section is this section here, and the slope is negative again, right? So it's going down, so the slope would be negative. So I'll put a negative there. And so that just kind of tells me where the function is going to be, where the derivative function is going to be. So I'm going to start somewhere on the negative side over here. Let me see. Okay, so I'm going to start on the negative side with the derivative. And it's probably not that, this is kind of shallow right here, so maybe a little more like that. Okay. And then it's going to turn to positive, right? Here it's positive. It looks like it's steepest about at that point, and then it kind of comes back down to, it starts to go back and turn to 0, right? So it's going to go up and then come back down, right? And here we hit 0 again. And on this side, it's a negative slope, so it's going to be below the x-axis, so it's going to go something like that, right? Okay, so that's what the graph looks like, and I might be a little off. Maybe that's not. Maybe this is more symmetrical than I made it look, but that's the basic idea: is find your zeros first, okay, by locating your peaks and valleys, and then plot those zeros on the graph, and then determine, okay, where is the graph? What is the graph on either side of those zeros, right? Is the slope negative? Is it positive? And you can just evaluate that by looking at the original function and seeing if the function is trending down, that's a negative slope, or trending up, that's a positive slope, right? All right, so that's how you graph derivatives given a sketch on a graph, and we'll do a Desmos activity that helps us kind of practice this and get some kind of virtual hands-on on that activity.